So my name is Varvara Apostolopoulou Kalkavoura, and I will present you today my PhD thesis entitled Thermal Conductivity of Hygroscopic Foams based on Cellulose Nanomaterials. So many friends already asked me, why did I use this as a cover image? And the answer is simple. It's because the snow has pores and it's an insulating material, and it's because it's a nice icebreaker image to start my presentation. So we are aware, as Tatiana said, that the energy consumption for the residential sector is gradually increasing and accounts for a large share, 22% of the global energy consumption, as well as the share of the CO2 emissions are also very large, and especially if we include also the non-residential area. Specifically for space heating and space cooling, it accounts for about 10% of the global energy consumption, and it can be up to 16% if we also include the commercial buildings. So there is an imperative need today to reduce the energy consumption and therefore to introduce materials with special properties and high performance that they can have thermal conductivities below air. So thermal insulation materials are porous, and in porous materials, the heat transfer is accomplished by either convection, radiation, or conduction. For the porous materials that I'm going to talk today, convection is negligible because we have usually pores below 1 millimeter, and the radiation is also considered rather negligible because we are talking about room conditions or climatic conditions, and it is known that the radiation escalates with the temperature. The gas conduction is maybe the most important, as it accounts for more than 60% of the total heat transfer within a porous material. In the large pore, we have the collisions between the gas molecules that drive the heat transfer. But if we manage to reduce the pore size below the mean free path of air molecules, then the heat can dissipate on the interface of the foam. Furthermore, the solid conduction, which is driven by phonons in case of insulators that are energy quanta that cause atomic lattice vibrations, is very important in case of nanostructured materials because of the numerous interfaces that are introduced that can act as diffuse phonon scattering sites and reduce even further the solid conduction contribution. So the insulation materials we are using today are either fossil-based like polyurethane and polystyrene, or they are like mineral wool, but they have moderate thermal conductivities. And recently the silica aerogels are emerging, but they have very low thermal conductivities below the super-insulating level, and they are rather promising, but they are also brittle and currently expensive to produce. Therefore, we consider cellulose as a possible candidate, as it is one of the most abundant biopolymer on Earth, and it can be found in wood, in algae, in tunicates, and many other sources. Wood constitutes one of the major sources, and if we use the wood pulp by different chemical and mechanical disintegration ways, we can obtain cellulose nanofibrils and cellulose nanocrystals that can be used further on for the production of foams and aerogels, and then they can be used for thermal insulation, for example, in buildings or packaging applications. One very interesting property of cellulose that we didn't look so much until now, it's anisotropy. Cellulose consists of covalent bonds along the fibrils direction, while it has weaker interactions in the perpendicular directions like hydrogen bonds and van der Waals. So in the context of this thesis, I designed and used an enclosed measurement cell in order to perform the thermal conductivity measurements in conditioned relative humidity and temperature. So there are several apertures on the top for the inlet and outlet of the humidified air, but also an aperture for the delta T sensor that measures the temperature variations within our cell, but also a relative humidity and temperature sensor that measures accurately the conditions in our cell. Importantly, we have an aperture on the side for the transient plane sensor, which is then connected to the hot disk device, which is a transient technique to measure the thermal conductivity. And this sensor is sandwiched between two foam pieces, as you can see in the image here. And in order to ensure that we have good thermal contact between the sensor and the foams, we add a small weight on the top. And then this enclosed measurement cell is dipped in an oil bath in order to ensure that the temperature is also well regulated. So the scope and the goal of this thesis was to evaluate and measure the thermal conductivity through experiments, simulations, and modeling and connect the anisotropy, the particle type, the moisture uptake, and the density, and see how those properties affect initially the thermal conductivity of foams based on cellulose nanomaterials. So I will first start with one type of foams, the anisotropic foams, that they are made by freeze casting and freeze drying of aqueous dispersions of cellulose nanomaterials. And here we had a mold that had a copper plate and Teflon walls, and it was placed on the top of a dry ice plate. And then we had unidirectional freezing from the bottom to the top, that along the freezing direction, the particles aligned, and this was proved by X-ray diffraction experiments. And as you can see, we had two different sides. The alignment side, as you can see here from the SEM image, that shows packed foam walls aligned along the freezing direction. And we had also macroporous cross sections that they looked more honeycomb-like in case of cellulose nanofibrils, and more elongated lamellar in case of cellulose nanocrystals. The foam walls, they were in all cases quite thin. In this case, they were 200 nanometers only, and they could be up to several micrometers depending on the density. So then moving to paper one, that is made with the same logic of freeze casting and freeze drying, we had three different grades of nanofibrils. But the first one was made by only mechanical disintegration in a grinder, and the other two, they were made also by moderate and highly temp oxidation. And here we can see the evolution in the diameter by the AFM images. And we obtained a diameter of around 2.3 nanometers for the highly temp oxidized sample. And also you can see that this sample, the highly temp oxidized, had very ordered honeycomb structure due to the repulsion forces that increased with the increasing charge density. So the thermal conductivity of those structures was strongly anisotropic, and we also observed that the fibril diameter, as it increased, led in more isotropic structures, that they had higher radial thermal conductivity and lower axial thermal conductivity. Interestingly, even if the thermal conductivity in the axial direction increased as a function of increasing relative humidity, in the radial direction, which is the super-insulating one and of interest for us, it didn't show the same behavior, while it showed the non-linear parabolic behavior as a function of the relative humidity, and we obtained the lowest value at 14 milliwatt per meter Kelvin at 35% relative humidity and 295 Kelvin for the highly temp oxidized sample. And this behavior was totally reversible. So in order to understand what is happening within our materials, we first did some gravimetric moisture uptake experiments that we confirmed that indeed increasing the relative humidity of course leads in higher moisture uptake for all three grades of CNFs. And then we also measured the swelling and the interparticle distance between two adjacent CNF particles by introducing the BGH's pore volume that we measured in nitrogen sorption experiments. And then this behavior of increasing moisture content could easily explain the axial thermal conductivity, but still it couldn't explain the radial thermal conductivity. So then we had to go one step further and collaborate with a group of Professor Yunishiro Shiomi. And here you can see two cellulose slabs that they're separated by a gap, and either the gap was kept constant and we increased the water in between of the two cellulose slabs, or the water was kept constant and the gap was increased. So then those simulations revealed that while the water content was constant and the gap was increasing, we had a disruption in the phonon bridges. So the thermal boundary conductance decreased significantly, while when the gap distance was fixed at 6 angstrom and we increased the water content in between of the fibrils, then because of the reformation of the phonon bridges, we observed increase of the thermal boundary conductance. And this behavior could be easily related to our experimental data, where we see that below 50% relative humidity, it dominates the swelling that causes increase in the interparticle distances, while at the humidity is above 50%, we have been observing that the replacement of air with water caused a slight increase, but in all times keeping the thermal conductivity below the super insulating level because of this competing mechanism. So then moving to paper 2, that it was also made with the same logic of freeze casting and freeze drying, but with cellulose nanocrystals. At the beginning, we wanted to study the density effect using cellulose nanofibrils, but we were very limited by the early gelation of the cellulose nanofibrils, that it doesn't help us to increase the dispersion concentration and thus the foam density. By using cellulose nanocrystals, we obtained foams up to 130 kilogram per cubic meter, but they also had macroporous structures, and they had also thin foam balls that escalated a little bit with the increasing density. They were also very anisotropic, as it was proved by X or D experiments, and if they picked at 40 kilogram per cubic meter, the orientation parameter, while it was quite low for the very low density foam, because it was rather fragile and the particles couldn't pack very well in the foam balls. And then because of the formation of the liquid crystalline phase in dispersion, we assumed that the particles were locked in certain locations and the orientation decreased. Interestingly, the nanopore volume increased at the beginning, peaking for the foam at 35 kilogram per cubic meter, meaning that increasing the solid content at the beginning makes the small pores to appear due to the small spaces in between of the fibrils or the crystals in this case. But then it decreased significantly afterwards. So the thermal conductivity was strongly anisotropic, and as Tatiana already mentioned, we can observe the typical U-curve for the radial thermal conductivity, which is not very obvious here, but we see a drop at the beginning. We reach a minimum of 24 milliwatt per meter Kelvin, and then we have an increase, a plateau, and further increase of the thermal conductivity because of the increase in the solid content. In the axial direction, we have a steep increase at the beginning and then mostly a plateau, and we assume it's because of the loss in the orientation. So it's very interesting to say that we obtained the very low value of 24 when we had the highest nanopore volume, meaning that the Knudsen diffusion that happens within the small pores indeed dropped the thermal conductivity a little bit to reach thermal conductivities below air. In order to understand the whole picture, we also did some theoretical estimations based on a simple serial addition of the main thermal conductivity contributions multiplied with their respective volumetric content. And then you can see here that we have two different options, the dry and the wet, and they were not too different in reality, but they were too far in case of the radial from our experimental values because we didn't include any confinement effects. However, for the axial direction, they overlap for low densities, but then we have higher deviations for the high densities. And this is because the model does not include the orientation parameter. And here we had a great loss in the orientation degree. So then moving one step forward, we decided to include those confinement effects by incorporating the Knudsen number and the Knudsen diffusion that happens in the small nanopores. And therefore, we calculated the respective thermal conductivity contribution. But even if it is an important parameter that we said that it's affecting a lot our data, it didn't really show that it's the main parameter to drop significantly the thermal conductivity. Therefore, another parameter, which is actually the number of interfaces in a nanostructure that can be translated by the interfacial thermal resistance, was even more important because it increased a lot the chances of diffuse phonon scattering at the interfaces. And therefore, by instead using the bulk thermal conductivity, by incorporating the interfacial thermal resistance, we obtained the red curve that seemed to have to be very close to our experimental data, having bigger deviations for the high density due to the loss of the alignment that is not part of this equation. And the small deviations here, we think, are because of the phonon scattering that happens in the solid air interfaces, or the foam wall variations that are not included in the model. So even if Knudsen diffusion is important, the presence of the interfaces is even more important to reduce the thermal conductivity of a bulk material towards a nanostructured material. So having the same principle of freeze casting and freeze drying, here we focused a little bit on the moisture uptake, And we wanted to actually compare the crystallinities, the surface modifications, and also to see what happens in other temperatures. So we had one tempo-oxidized cellulose nanofibril foam, tempo-oxidized cellulose nanocrystals, and a carboxymethylated cellulose nanofibril sample. So in all cases, the moisture uptake increased with increasing relative humidity. And we observed that for higher crystallinity samples, the moisture uptake was lower. And in collaboration with a group of Professor Igor Zuzulenko, we also examined some simulated materials, one amorphous cellulose film and one crystalline cellulose bundle, and we observed the same behavior, that the crystalline sample had a lower moisture uptake due to the rigidity of the structure that doesn't let the water molecules to go in. So the same behavior was observed also for the carboxymethylated samples. But interestingly, when we increase the temperature, even if the water in the air is more in higher temperatures, the moisture uptake decreased significantly for both the experimental and the simulated samples. So what happens here is that an amorphous samples has more entering points, since it has more pores compared to a crystalline structure that has stronger bonds and a rigidity of the structure. So in case of an amorphous sample, the water that can penetrate is always more because of the more entering points. When we increase the temperature, in both cases, we saw the moisture uptake was lower. And what happens is that in case of an amorphous sample, the pores are getting less, so there are less entering points for the water. But in case of a crystalline sample, the water prefers to stay at the interfaces, and only a small portion goes inside the crystal structure. And therefore, what we see at higher temperatures is that we have less number of water molecules around the hydration cell of the oxygen of the carboxyl group. So then moving to a different category, the isotropic foams that were made by foaming and oven drying. Here we had cellulose nanofibrils foamed together with a surfactant P123 and together with gluconic acid and calcium carbonate to enhance the cross-linking within our structure. After oven drying the structure, we obtained isotropic macroporous foams that when we tested the thermal conductivity against the temperature, we had a small increase, while the increase was very large as a function of relative humidity, and it escalated with increasing temperature. It's worth mentioning that it was around 87% at 295 Kelvin. And this was because of their hygroscopic character. They managed to reach 26 weight percent at 80% relative humidity. However, if those materials, even if they are moderate insulators, we managed to predict their behavior by a modified Kunzel's model. We found that the thermal conductivity has a linear behavior with the moisture content by mass. And then we feed our data to this modified model that was made for low density materials compared to the materials that studied by Kunzel, that they were cement or wood and they had very high densities. And then we also measured the water vapor permeability using the dry cup method in a humidity chamber. And then we calculated afterwards the moisture resistance factor. And we observed that the moisture resistance factor was much lower than those from Kunzel. So then the modified model was able to predict the thermal conductivity of low and high density foams, that they were rather low density in general, and with low moisture resistance as well. So then moving to another type of isotropic material that was made by freeze drying in this case, we used Kalkavoura cellulose, and we ion exchanged the fibers with aluminum ions, and then we activated to the surface by using PVP. And this job was done in collaboration with Cao Xu from Uppsala University. And by dipping them in the mixture of the organic ligand and the aluminum salt, we enhanced the nucleation and growth of the MOF almyl 53. And then by freeze drying the aqueous dispersions, we obtained dry foams. And then we enhanced further nucleation of the almyl 53 by dipping them again in the mixture of the organic ligand and the aluminum salt and freeze drying. Those structures, because of the microporous structure of the MOF, they had the hierarchical pore structures consisting of micro, meso, and macropores. And by measuring their thermal conductivity, we observed that the thermal conductivity of the hybrids was lower than the thermal conductivity of the pure MOF, of course, but also lower than the thermal conductivity of the pure CNF foam. And also the moisture uptake of those materials, they were also lower than both the composite of cellulose nanofibrils and pluronic and the pure CNF foam, showing that by incorporating a microporous and simultaneously hydrophobic agent in our foams could lead in lower thermal conductivity, improving the properties. And even if they are moderate insulators, they could be used, for example, in packaging applications. Moving then to the conclusions, we managed to prepare anisotropic foams of cellulose nanofibrils that they had packed foam walls and honeycomb macroporous cross sections, and they were super insulating for a wide range of relative humidities and densities. And we obtained the very low thermal conductivity of 14 milliwatt per meter Kelvin at 35% relative humidity and 295 Kelvin. And all this happened because of the competing mechanism between the swelling that causes an increase in the interparticle distance and disrupts the phonon bridges, while at humidities above 50%, we have the replacement of air with water that increases a little bit the thermal conductivity due to the reformation of the phonon bridges. But the whole picture is that we have this competition that keeps the thermal conductivity below the super insulating level. Instead of cellulose nanofibrils, we use cellulose nanocrystals because we were limited by the gelation of cellulose nanofibrils, the early gelation. While with cellulose nanocrystals, we managed to achieve densities of dry densities as high as 130 kilogram per cubic meter. And those foams that had the lowest thermal conductivity had also the highest nanoporosity, showing that the Knudsen diffusion that happens in the small pores has indeed an effect in reducing the thermal conductivity by minimizing the collisions and dissipating the heat at the interfaces. However, the major mechanisms that reduces the thermal conductivity of a bulky material towards a nanostructure is the amount of interfaces that can act as possible diffuse phonon scattering sites that reduce significantly the solid conduction contribution and thus the total thermal conductivity. Moving on to paper 3, here we had a combination of simulated samples and experimental samples. And in all cases, the more crystalline the sample it was, the lowest the moisture uptake it was, because amorphous samples have more and larger pores, while a crystalline structure is more rigid and doesn't have so many access points for the water. At higher temperatures, both crystalline and amorphous samples, they had lower moisture uptake due to the reduced chemical potential of water, but specifically in case of amorphous film, we had smaller pores, and in case of crystalline bandle, we had less water molecules attached around the hydration cell of the oxygen of the carboxyl group. So moving to a different category of poorer insulators, here we had isotropic foams made by cellulose nanofibrils and pluronic, and they showed a small temperature dependence, which is good, but they had rather strong relative humidity dependence up to 200% at 40 degrees Celsius. But we were able to model those structures and predict their behavior by a modified Punzel's model that took into consideration that they were low density foams and with low moisture resistance. By incorporating a hydrophobic microporous agent like the Almil 53, we were able to have lower moisture uptakes than the previous foams or the pure CNF foams, and also lower thermal conductivities, opening and paving the way that hydrophobization, it could be a way to reduce the thermal conductivity. So in this case, we evaluated the thermal conductivity and measured it, and we connected the anisotropy, the particle, the moisture uptake, and the density, but also we found several interconnections between those properties. However, there were still some question marks, but they always exist, and this is why future work is always needed. So I would suggest that we could study further on the temperature dependence of anisotropic foams, because they're very interesting and super insulating, and we want to use them in different climatic conditions. we can maybe use more environmentally friendly processes like oven drying, and we can enhance cross-linking and hydrophobization, both to reduce the moisture uptake, but also to enhance the fire retardancy and mechanical robustness. As we said in our recent review, the multi-scale materials are also of great interest because of mismatch in the phonon interfaces and the phonon scattering, which could even more reduce the solid conduction contribution that was found to be the main mechanism to reduce the thermal conductivity. And even if we had some generous modeling approaches in this thesis, I would suggest that more modeling is needed to predict in detail the behavior of such hygroscopic materials and to upscale such materials and use them in real life applications. So at this point, I would really like to thank the Swedish Energy Agency and the Wallenberg Wood and Science Center for funding this project. And I would really like to thank my supervisor, Lennart Bergström, for supporting me all these years, and all of the co-authors that contributed in this thesis. But also I would like to thank all the participants of today, Tatiana, the opponent, Monica, Annette, and Javier from the committee, and Ulrich and Gunnar from Stockholm University. Thank you for your attention.
Thank you very much, Varvara. And now we will take a 5 minutes break, so we will come back at 13.51. Yeah?